The Yagiuda antenna is named after the inventors Professor S. Huda and Professor H. Yagi around 1928. The Yagi comes from the inventor whose name is Professor H. Yagi. Similarly, the Huda comes from the inventor whose name is Professor S. Huda, and they named this antenna in 1928 as Yagiuda antenna. This is in short form known as Yagi, and it is an end fire antenna which is widely used in VHF and UHF bands. Means it is used in 30 megahertz to 3 gigahertz. This antenna is most famous because of its simplicity, low cost and relatively high gain. It consists of three different elements. The first one is driven element, second one is reflector, and the third one is director. And the basic element that is used in Yagi is lambda by 2 dipole, which is placed horizontally, and it is known as the driven element or active element. And in order to convert the bidirectional dipole into a unidirectional system, the passive elements are used, which include reflector and director. The passive or the parasitic elements are placed parallel to the driven element, collinearly placed close together. The Yagiuda antenna is named after the inventor Professor S. Huda and Professor H. Yagi. The Yagiuda antenna is also known as Yagi, and it is an end fire antenna. It is basically used in VHF and UHF bands. VHF and UHF bands. It consists of three main elements: the driven element, reflector, and the director. And the driven element is the one which is a lambda by 2 dipole, which is placed horizontally, and it is also called as active element. And to convert the bidirectional dipole to unidirectional system, the passive elements are used, which include reflector and director. And these passive or parasitic elements, they are placed parallel to the driven element, collinearly placed close together. Slide. The parasitic element which is placed in front of driven element is called as director. The parasitic element which is actually placed in front of the driven element is called as director, and this is having a length less 5% less than the driven element. And one which is placed at the back of the driven element is called as a reflector, and it is having length 5% more than that of the driven element. The one which is placed in the front is called as a director, and it is having length 5% less than the driven element, whereas the element which is placed at the back of the driven element is a reflector, and it is having length 5% more than that of the driven element. And coming to the spacing between the element, it ranges between 0.1 lambda up to 0.3 lambda. And for a 3 element system in the sense whenever there is a driven element, director and reflector, one each in number, we have got it. Now coming to the length of each, the reflector length is 500, the driven element length is 475, and the director length is 455. As I just told about the length which has to be maintained for the director and the reflector, the director should be having the length 5% less than the driven element. So, if the driven element is 475, the director length will be 455. Similarly, when we tell about reflector, it is having a length 5% more than that of the driven element. That is why, since the driven element length is 475, this reflector length is 500. Now, with these parasitic elements, the impedance reduces less than 73 ohms and may be even less than 25 ohms. And in order to increase the impedance, a folded lambda by 2 dipole can be used. Generally, with these parasitic elements, the impedance reduces less than 73 ohms and it can be even less than 25 ohms. And whenever we use a folded lambda by 2 dipole, this impedance can be increased. And the system may be constructed with more than one director. And whenever we use more than one director, addition of each director increases the gain by nearly 3 dB. So, whatever directors we use, they are nothing but the amplifiers. It increases the gain. and each director increases the gain by nearly 3 decibels. Now the number of elements in a Hagi is limited to 11. It means totally the reflector, driven element and directors should be equal to 11. Now let us know the basic operation of this Yagiuda antenna. And as I just told about the three important elements of the Yagiuda antenna, they are driven element, the reflector and the director. And if we want to define these three elements, we can define this each individual elements as the driven element is a Hagi antenna element to which the power is applied, and it is normally a off-wave dipole or often a folded dipole. Coming to the reflector, the Hagi antenna will generally have one reflector. This will be behind the main driven element, and this gives a slight improvement in the performance, reducing the level of radiation or pickup from behind the antenna, that is in the backward direction. It will actually reduces the level of radiation, and typically a reflector will add around 4 or 5 decibels of gain in the forward direction. Now coming to the director, the directors will be placed in front of the driven element, and typically each director will add around 1 dB of gain in the forward direction, although this level reduces as the number of directors increases. The phases of the currents in the parasitic element depends upon the length and distance between the elements. Whenever we tell what is the phase of the current in this parasitic element, it basically depends upon the length and the distance between the elements. And the parasitic element of length, which is greater than lambda by 2, is inductive, which lags, and of length less than lambda by 2 is capacitive, which leads the current due to the induced voltage. Whenever the parasitic element is having length which is greater than lambda by 2, we tell that it is inductive, which is inductive. It means the director is inductive and it lags, whereas the one which is having length less than lambda by 2 is capacitive. It means we are speaking about reflector, which leads the current due to the induced voltage. Now the properly spaced elements of length which is less than lambda by 2 act as a director and add the fields of a driven element. Each director will excite the next. The directors resonates slightly higher in frequency than the driven element. Coming to the reflector adds the fields of driven element in the direction from reflector towards the driven element. The reflectors resonates slightly higher in frequency than the driven element. I repeat, the properly spaced elements of length less than lambda by 2 act as director and add the fields of a driven element. Each director will excite the next. The directors resonates slightly higher in frequency than the driven element. Similarly, the reflector adds the fields of driven element in the direction from reflector towards the driven element. The reflectors resonates slightly higher in frequency than the driven element. The greater the distance between driven and directed elements, the greater the capacitive reactance needed to provide correct phasing of parasitic elements. As the length of element is tapered off to achieve the reactance. And we can tell that this Yagiuda antenna is a directional antenna with adjustable front to back ratio. This is very important with respect to the Yagiuda antenna. It is a directional antenna with adjustable front to back ratio. This is how the Yagiuda antenna looks like. The middle one is the lambda by 2 dipole, which is a driven element, and this the one which is present behind this driven dipole is a reflector which is having length equal to capital L REF reflector, and the spacing between these two, that is the reflector and the driven element, should be capital S with the suffix REF. Next element is the director. There can be more than one director, and these are having length which is less than this driven element, and the length of the driven element is represented as capital L DIR. These are the directors, and the directors are having length less than the driven dipole, and it is capital L DIR. and the spacing between these directors is capital S DIR. And this is how the pattern, E-plane pattern of the Yagiuda antenna looks like. The radiation pattern is more directed in the right direction, and there is a minimum value in the left direction. It means the radiated value, the reflected value is least in the left direction compared to the right direction, because it is a unidirectional antenna. Now, let us know the typical values of the Yagiuda antenna. Whenever I tell director length, the director length is in the order of 0.4 to 0.45 lambda, and the recommended value is 0.43 to 0.44 lambda. Similarly, the feeder length, which is usually a folded dipole, is having a dimension equal to length equal to 0.47 to 0.49 lambda, and recommended value is 0.48 lambda, which is equal to L plus D. Similarly, coming to the reflector length, it is in the order of 0.5 to 0.2525 lambda, and the recommended value is 0.49 to 0.51 lambda. And coming to the reflector feeder spacing, what is the spacing between the reflector and the feeder? It is in the range of 0.2 to 0.25 lambda. And coming to the director spacing, the spacing between the individual director should be 0.3 to 0.4 lambda. The standard recommended value is 0.25 to 0.3 lambda. Now, let us discuss about the graphical representation of directivity with respect to the number of elements. As I told, the number of elements is limited to 11. Starting from 1 to 11, whenever the number of elements are being taken in the Yagiuda antenna, how actually the directivity changes, that is what we need to analyze with respect to this graph. As you can see, when the number of element is 1, the directivity is least. As it increases 2, as it increases 3, as it increases to 4, as it increases to 5, as it increases to 6, like that. When it increases up to 11, with respect to the number of reflectors, how many reflectors we take, how many directors we take, depending on that, we get 1 dB more gain, and if we are using 5 reflectors, means we get 5 dB more gain, and the directivity actually increases. And as you can see here, the gain is 1 to 2 dB less than this value. It means here, when I cross this value, that is the standard representation taken with respect to 3, number of elements is 3, means just one director, one driven element, one reflector. We have got the gain in the directivity in the gain of 8, directivity in the range of 8. And as it is increased further, there is only a slight increase with respect to, means as you can see 1 dB, we will be having 1 dB slight increase with respect to the directivity. Now, let us discuss about the characteristics of the Yagiuda antenna. These are the characteristics of the Yagiuda antenna. The Yagiuda antenna is basically used for high frequency, very high frequency and UHF bands. And the main advantages of this is it is having high gain, and it is very simple to use. It is having low weight, low cost, and it is having a relatively narrow bandwidth, and a unidirectional beam with a moderate directivity. And the bandwidth increases between 2% when the space between the elements ranges between 0.1 lambda to 0.15 lambda. And it provides a gain of 8 decibels and a front to back ratio of 20 decibels. The Yagi is also known as super directive or super gain antenna, since the system results in high gain. If greater directivity is to be obtained, more directors will be used, and array up to 40 elements can be used, and these arrays can be stacked to increase the directivity. And the Yagi is essentially a fixed frequency device. It means the frequency sensitivity and the bandwidth of about 3% only is achievable. Let us repeat the characteristics. The Yagiuda antenna is used for high frequency, very high frequency UHF bands. with the advantages of high gain, simplicity, low weight, low cost, relatively narrow bandwidth, and has unidirectional beam with moderate directivity. The bandwidth increases between 2% when the space between the elements ranges between 0.1 lambda to 0.15 lambda. It has a gain of 8 decibels and a front to back ratio of 20 decibels. Yagi is also known as super directive or super gain antenna since the system results in high gain. If greater directivity is to be obtained, more directors will be used, and arrays up to 40 elements can be used, and these arrays can be stacked to increase the directivity. Yagi is essentially a fixed frequency device, and frequency sensitivity and bandwidth of about 3% is achievable. This is how practically the Yagiuda antenna looks like. The whole antenna, which was actually used for our TV in the older times, that was actually a Yagiuda antenna. As you can see, this is the driven element. As you can see, the wire is actually connected to this driven element because this is the source through which the radiation will be generated, and the power supply has to be given to this driven element. And after this, whatever we are seeing whatever we are watching with respect to this, and which is having length which is less than the driven element, are directors, and the one is behind this is a reflector. And this was a Yagiuda antenna which was actually displayed, was invented by the person Yagi, and he just showcased that Yagiuda antenna. This is about the explanation with respect to the Yagiuda antenna. What is Yagiuda antenna, why it is named as Yagiuda, and what are the basic elements of the Yagiuda antenna, what are the salient features, and how the Yagiuda antenna works, what are the characteristics of the Yagiuda antenna. Let us end this session, and in the next session let us continue this with one more antenna. Thank you.